Ever wonder how something as chaotic as a gas with billions of molecules bouncing around can actually behave in predictable ways?
It's pretty mind-blowing, right?
It really is. And that's exactly what we're diving into today with statistical mechanics.
We've got some excerpts from Richard Feynman's legendary physics lectures.
And he was known for making even the most complex ideas surprisingly intuitive.
Exactly. Like, he starts with something we all know, the Earth's atmosphere.
Okay, so we've all felt that difference in temperature when we climb a mountain, colder at the top, warmer at the bottom?
Yeah, that's what we might intuitively think.
Right.
But Feynman actually challenges that assumption right away.
Oh, really?
Yeah. He says if there were actually a temperature difference at different heights in the atmosphere, we'd see something pretty interesting.
What do you mean?
Okay, imagine a rod connecting, like, molecules at the bottom of the atmosphere to those at the top.
Okay, so I'm picturing those bottom molecules bouncing around like crazy, full of energy because it's hotter down there.
Exactly. And they'd be constantly transferring that energy, that heat, up the rod to the less energetic molecules at the top.
Good.
And this transfer would keep going,
Okay.
right, until eventually the entire system would, like, reach this state of thermal equilibrium.
So everything would eventually become the same temperature.
Exactly. The temperature would be uniform throughout.
So even though it might feel colder as we climb a mountain, the temperature itself is surprisingly constant throughout the atmosphere.
Exactly.
That's counterintuitive.
It is. Now, that doesn't mean gravity doesn't play a role. It does. But it affects the distribution of the molecules, not the temperature variation with height.
Distribution.
Yeah.
Now, that makes me think about how the air gets thinner as you climb higher. Is that connected to this idea?
You're spot on. As you ascend, the density of molecules decreases exponentially with height.
Okay, so it's not just that there's gradually less air.
Right.
It's a rapid drop-off.
Like, imagine this. For every mile you climb, the air gets astonishingly thinner.
Exponentially.
Mm-hmm.
That's wild.
And here's where it gets even more intriguing. This principle isn't limited to gravity.
What do you mean?
Any force that acts on molecules, whether it's an electric field or something else entirely, will influence their distribution in a similarly predictable exponential way.
Huh. So there's this underlying mathematical elegance governing how molecules arrange themselves, regardless of what forces are acting on them.
You got it.
That's pretty mind-blowing.
And that elegant math leads us to one of the foundational concepts in statistical mechanics, Boltzmann's law.
This sounds important.
It is.
Okay, walk me through this Boltzmann's law. What's the core idea?
In essence, Boltzmann's law states that the probability of finding molecules in a particular arrangement depends on two key factors: the energy of that arrangement and, as we've already touched upon, the temperature.
So if I'm understanding this correctly, low energy arrangements are more probable.
You've got it. Lower energy equals higher probability.
Interesting. So it's kind of like molecules are inherently lazy.
You could say that. It's a fundamental principle that governs everything from the behavior of gases to how they transition into liquids and solids as temperatures drop.
Okay, now I'm really curious about how this plays out. Beyond just gases, they thin out in a predictable way, but liquids and solids, they behave very differently, right?
That's the beauty of it. This deceptively simple equation from Boltzmann, often involving e to the something, governs these transitions too. Imagine for a moment a single water molecule. At high temperatures, it's bouncing around like crazy with its fellow molecules, a gas.
Full of energy, maximum freedom.
Precisely. But as you cool things down, the energy decreases. And those lower energy states where molecules are closer together become more and more probable.
So they're more likely to stick together.
Exactly. And eventually, as the temperature continues to drop, the attraction wins out, and bam, you've transitioned from a gas to a liquid, and eventually a solid. And Feynman illustrates this beautifully using a clever thought experiment. He asks us to imagine just two molecules in a graph called a potential energy curve.
Okay, a graph representing the relationship between two molecules. That sounds intriguing.
It really is.
So what can we learn from this potential energy curve?
So this curve elegantly reveals how the likelihood of finding those two molecules at various distances, it changes with temperature.
Okay.
So picture this. On one axis, we have the distance between the two molecules.
Okay.
On the other axis, we have their potential energy.
I'm visualizing it.
All right.
So at high temperatures, what does this curve look like?
At high temperatures, the curve is relatively flat,
Okay.
meaning the molecules can be found at practically any distance along that axis with nearly equal probability.
Okay, so they're just like zipping around. They don't really care where the other one is.
Precisely.
Okay.
But here's where the potential energy curve takes an interesting turn.
Okay.
As you lower the temperature,
Yeah.
the curve develops a dip, well, at a specific distance.
A dip. So that's representing a change in energy then.
Exactly. That dip, signifies the distance where the potential energy between the molecules is at its lowest.
So they're more likely to be there.
They're more inclined to linger in that low energy, attracted to each other.
Ah, so that's where things get sticky, literally. They're more likely to be drawn together, hanging out in that low energy state.
Yes.
Interesting.
And Feynman uses this simple two-molecule model to beautifully illustrate the essence of condensation.
That's incredible. But I have to imagine that scaling this up from 2 molecules to, say, the billions found in a glass of water, that's going to make things exponentially more complex.
You're absolutely right, and that we arrive at what's known as the many-body problem.
Which doesn't sound simple.
No, it's not that it's bad, it's just mind-bogglingly complex.
Okay.
Even with elegant laws like Boltzmann's law, predicting the precise behavior of billions of molecules, each interacting with one another, is an immense challenge.
So even with these powerful tools, there are still mysteries to unravel in statistical mechanics.
Absolutely. That's what makes this feel so captivating.
Right.
There's always something new to uncover, something new to explore.
Okay, so we've discussed how molecules are distributed in space, but what about their actual movements? How do we even begin to comprehend the motion of billions of molecules?
Excellent question. While we might not be able to pinpoint the exact velocity of every single molecule at any given moment.
Because they're constantly colliding and changing speeds and changing directions.
Exactly.
Yeah, it's absolute chaos at that level.
Precisely. However, what we can do is determine how many molecules are moving within a specific range of speeds.
Okay.
This is where the concept of a velocity distribution function comes into play.
Velocity distribution function. That sounds like we're diving deeper into the math behind this.
We are.
Okay.
But before we get to the nitty-gritty of the math, let's revisit our trusty friend, the Earth's atmosphere.
Okay.
Feynman, with his talent for elegant explanations, uses this example to illustrate how we can derive the distribution of molecular speeds.
So we're using what we know about how the density of molecules changes with altitude to figure that out.
Exactly. He highlights how the fundamental principle of energy conservation underpins this entire concept. Molecules need a certain amount of kinetic energy, the energy of motion, to overcome gravity and reach higher altitudes.
Okay, I'm starting to see where this is going.
So by analyzing how many molecules possess sufficient energy to ascend to various heights, we can essentially work backward to figure out the distribution of their speeds.
So it's like using gravity as a giant speed trap.
Exactly.
I like that analogy.
Yeah.
But wouldn't all those constant collisions disrupt this beautifully organized distribution?
Yeah.
I imagine it'd be like a cosmic billiards game up there.
A very vivid image. And while you'd think those collisions would wreak havoc on the distribution, they don't actually disrupt things as much as you might imagine.
Why is that? I'm having trouble wrapping my head around how collisions wouldn't completely scramble the speeds.
It all boils down to the overall energy exchange within the system.
Okay.
Yes, individual molecules are constantly gaining and losing energy through these collisions. Yeah. But the distribution of speeds, the overall pattern, remains remarkably stable.
So even though individual molecules are changing speeds, the overall rules of the game stay consistent.
Perfectly put. And here's the truly elegant outcome. The probability of a molecule having a particular velocity can, once again, be represented by an exponential function.
There's definitely a recurring theme here.
It always circles back to that fundamental link between energy and temperature.
This is all fascinating, but how can we be sure these theoretical tools hold up in the real world? How do we put them to the test?
That's where things get really exciting. Feynman takes us from the theoretical realm into the laboratory and introduces the concept of specific heat.
Okay, I have to admit, specific heat is a term I vaguely remember from high school chemistry.
Yeah.
Could you give me a refresher?
Of course. In simple terms, specific heat is a measure of a substance's capacity to store energy.
Okay.
Specifically, how much energy is required to raise the temperature of that substance by a certain amount. There's a specific ratio, represented by the Greek letter gamma, that connects specific heat to how a gas behaves when it's compressed or expanded.
Okay.
This gamma ratio acts as our measuring stick, allowing us to see if our theoretical predictions match up with real-world observations.
So we're putting our theoretical calculations to the test,
It can put us
comparing
to...
them to experimental data.
Yeah.
What happens when we apply this measuring stick?
The results are incredibly intriguing. When we examine simple monatomic gases, such as helium, krypton, or argon, their behavior aligns almost perfectly with our predictions.
Wow.
The measured values of gamma match beautifully with the theoretical values we derived from those kinetic energy calculations we discussed earlier.
That's incredible. Our theoretical models, based on statistical mechanics, accurately predict the behavior of these gases in the real world. It feels like a huge win for classical physics.
It is a remarkable confirmation of the power and elegance of classical physics.
Yeah.
However, as we've encountered before, things don't always remain straightforward.
Oh no, here we go again.
When we shift our focus to diatomic gases,
Uh-oh.
molecules like oxygen and hydrogen,
Okay.
things become a bit more complicated.
Oh no, what's the catch with diatomic gases? This is where things take an unexpected turn, isn't it? What happens with diatomic gases?
Well, the predicted values of gamma, based on our classical model of these molecules, don't quite align with the experimental data.
So there's a discrepancy between what we expect to see and what actually happens.
Precisely. And it's a discrepancy that even Feynman grappled with.
Oh, really?
He openly admitted that he couldn't reconcile classical physics with these experimental observations for diatomic gases. He couldn't explain why they weren't behaving as the classical model predicted.
So even Feynman, a giant in the field of physics, hit a wall.
Yeah, it's pretty amazing, right?
That's both reassuring and a bit daunting.
What's fascinating is that these walls often signal that we're on the cusp of a significant breakthrough.
Interesting.
This inability to fully explain the behavior of diatomic gases using classical physics hinted at the need for a revolutionary new perspective.
This is where quantum mechanics enters the picture.
You guessed it.
Yeah.
But that's a journey for another deep dive. The key takeaway here is that even when our existing models fail, those failures can be incredibly illuminating.
So it's like those failures push us forward.
Exactly. Feynman's struggle highlights how crucial it is to question assumptions and embrace the unknown. Those moments when our understanding falters can lead to the most profound discoveries.
It's about pushing the boundaries of our knowledge and being open to completely new ways of thinking. We've covered a lot of ground in this deep dive.
We have.
We've journeyed from the predictable chaos of gases to the intricate dance of molecules, all guided by the elegance of statistical mechanics. It's really pretty incredible.
And it's important to remember that statistical mechanics isn't just about understanding gases in a container.
Right.
Its principles extend far beyond that, allowing us to comprehend the behavior of stars, the mysteries of black holes, and even the fundamental nature of the universe itself.
It's amazing to think that the same principles governing the air we breathe also apply to the vastness of space. It really highlights the interconnectedness of everything.
Precisely. And that's the beauty of physics, uncovering the underlying principles that unite seemingly disparate phenomena.
This deep dive has certainly left me with a sense of awe and a thirst for more. To our listeners, if you're eager to explore how quantum mechanics revolutionized our understanding of statistical mechanics and delve deeper into the fascinating world of atoms and energy, be sure to join us for our next episode. Until then, happy exploring.